So, all right. So now we need to talk about another sort of mathematical construct called the magnetic flux. Okay, and so the magnetic flux is just defined, so the symbol for it is this sort of like capital I with a circle drawn through it, and then subscript B. And it's basically like the way I think of it is it's the amount of magnetic field that is going through a specific area. Okay, so if I think of like that loop, right, and I have a current going through that loop, there's going to be a magnetic field, right, that is going to be perpendicular to the loop. The flux is the field times the area times cosine theta. So the flux is going to be maximized when the field lines are going in the same direction as the area vector. Does that make sense? So let's say that I've got this loop, but it's not connected to a power supply. Right? It's got no current going through it. And I've got this external magnet, right? And the external magnet obviously has a magnetic field, right? And I orient the magnet so that the field lines are exactly perpendicular to the loop, right? I could calculate the flux of that loop just by multiplying the magnetic field lines times the area vector times the cosine of the angle between them, which, if they're in the same direction, is just going to be 1, right? Because cosine of 0 is 1. Does that make sense? So like you can see here, the area vector, remember, is perpendicular to the area of the loop, right? If I've got my magnetic field lines going in that same area, then I would calculate the magnetic flux just by multiplying the field times the area vector times cosine of theta, which would be 0 in that case because there's no angle between them. So it would be just B times A. So the stronger the field, the larger the flux. The bigger the loop, the stronger the flux. Does that make sense? Does anyone have any questions? This is kind of just showing that exact same thing, but in lots of different ways. So let me ask you this. If I had, let's say I had a loop like this, and I know the area vector is always perpendicular to that, so that's the area vector. And let's say now my field lines were going like this. This was my external magnetic field, like that. What would be the magnetic flux? 0. Right? Because you would have 90 degrees, cosine of 90 is 0, so there'd be no magnetic flux. So there has to be some component of the magnetic field that is going in the same direction as the area vector in order for you to have flux. Okay, so you could have like an angle, like it's shown here. You could tilt the magnetic field, but there's still going to be a component of that field that is in the same direction as the area vector, and therefore you still have flux. Okay, can flux be negative? What do you think? Just looking at the mathematical equation, can you have a negative flux? Yeah, for sure. If you have a loop and you define your area vector as this way, right, but your magnetic field is this way, then that flux would be negative, right? So flux, it would be a negative value. Right? Because it would be like, instead of cosine of 0, it would be cosine of 180 degrees, and that's a negative. Okay, so does everyone sort of have a general sense or like an understanding of what flux is? Okay, so there's sort of 2 topics left to discuss, and they're intricately connected. So the first is Faraday's law. So basically what Faraday's law says is if you have a change of flux through a loop, you can induce a current in the wire. So like here, and we'll show, we've got it set up at the front here. We'll show you in a second. But here I've got just a wire. It's not connected to like a battery or anything. It's just a straight wire in a coil. So there's wire, coil, going back to this meter that is basically measuring current. Okay, so this is, it's called a galvanometer, but it just measures current. Okay, and if I take just a simple bar magnet and I change the flux of the loop, so I'm changing the magnetic flux, I can induce a current in that loop. Okay, I've got actually a little simulation here that you can play around with. The link for it is on the page there. You can download it and play with this. But this is basically like a coil of wire. It's not connected to a power supply at all. It's just a simple wire coil. And it's connected to a bulb. Okay, and here I've got a magnet. And if I move the magnet, if I move the magnet relative to the coil, you can see that I induce a current in the coil, and that lights up the battery. Right? And there's all sorts of things you can play with here. You can change the strength of the magnet. Right? If you change the strength of the magnet, what do you think that does to the flux? It increases the flux. Right? So if I increase I can change that. I can get like a huge current, right, by changing the flux that way. If I made the area of the wire bigger, I thought there was a way of doing that, but maybe. Oh yeah, if I change the area of the wire, I also increase the flux, right? Okay, and then there's another sort of fun thing that you can play with here. And this is actually how electrodynamic sort of generators work, right? If you've got like a water supply like pouring over some mechanical thing that it sort of flips like as the water is pouring over it, and that thing is attached to a magnet, and the magnet is sort of rotating around as a result of the water flowing, and you've got this other sort of coil that's nearby, you can generate current. You can generate electricity. This is how like hydroelectric dams work, right? By sort of having water turning some magnet and then a coil of wire nearby. Okay, so I encourage you to try that out on your own later. But let's show you the demonstration. And then we'll talk about some of the math behind it.